Okay, I'm back, and you can hear me, hopefully. Apologies for that. Hopefully that'll be the last time that happens, but we'll see. So go to the whiteboard, share, bingo. So the whiteboard happened, hopefully, and you're all looking at a big empty space. So to Josh's question, several of the ranges have the property that the range is deliberately set to be false. Whoa, man. This is set really weirdly. Okay, we're going to type. Tablet is not configured correctly, and I don't want to take up your time with futzing it with it. So today we're going to type, and I apologize. If we have even, let's make black would be better. If we have even.I and odd.I, as Josh pointed out, that is just false. Like a number can't be both even and odd. And so that just simplifies to false, in the same way that if we had I less than 0 and I greater than 0, that would simplify to false. And that happens actually more often than you might think, where expressions end up simplifying to something like true or false. And in this case, a lot of these in that particular quiz problem do simplify to false, which then leads you to the empty range rule, because the empty range rule is the situation where the range is false. So trying to find where is looking for the empty range rule, and I'm totally failing to find it because apparently I'm not capable of reading. But it is the case that if you have, so, and this is meant to be star, not multiplication. If you have something like that, this is going to equal U, where U is the identity of the operator star, whatever that operator is. So this is saying if we have false here, this thing will collapse down to the identity. So it's important to be able to recognize when the range is false, and to know the identity of the operators. So that's another question that tends to come up in this situation. So if we do, I'm going to start it over here, make a little list. Oh, stop it. No, fine. The identity, so if we have operator and identity, so if the operator is plus, 8.13. Oh, that's why I was looking at the wrong page. It was the very first of the chapter 8 rules. Thank you. I appreciate that. So Noah found the rule I was looking for. So that's 8.13. So I can put that here. Oops, no. So if we have the operators plus, the identity for plus is 0. Whoops, 0. Oh, gee whiz. And it's 0 because x plus 0 always equals x. That's what it means to be an identity operator, is that when you apply the operator to that value, you don't change things. And so times is 1, because x times 1 is x. And then the two that matter the most at the moment in the class are and or. And is true because P and true equivals P, right? That's a chapter 3 rule, which I won't bother looking up. And or is false because P or false equivals P, again, a chapter 3 rule, which I won't bother looking up. And then max is minus infinity, and min is plus infinity, if we ever end up caring about those. But those are sort of the 4 operators that most easily do something with the chapter 8 rules, because they're all symmetric. Symmetric, they're associative, and they all have an identity. And so that allows us to use things like rule 8.13. So if the range is false, then the quantifier collapses to being just the identity of the operator. Okay. And that's, it might not seem super obvious that that would be what you would do. It turns out it works. So that's one argument for it. It's also, in some ways, it does kind of make sense. Like if I say, I hand you a box of numbers and I say, add up all the numbers in that box. If the box is empty, saying the sum is 0 isn't insane, at least. Because it's like, oh, there weren't any numbers, so we'll just say the sum is 0. Well, in the same way, then it turns out that saying that the product of an empty box of numbers is 1. For and or, one way to think about it is, if I say everybody who's at the meeting has a nickel, if there's no one at the meeting, then in some sense it's kind of, in a vacuous way, true. It is true that everyone in a set of nothing has a nickel. Like if I point at all the people in the room and say that person has a nickel and that person has a nickel, if I don't have to point at anybody, then it's sort of true in a kind of weird way that yes, everyone in an empty set has a nickel. And in the case of or, you're saying there exists somebody that has a nickel. And if you think about exists, like if I say someone in the meeting has a nickel, it would be reasonable for you to say who has a nickel. If you claim someone does, tell me who they are. And I ought to be able to do that. If I genuinely know that somebody has a nickel, I ought to be able to say, oh, I think Ellis has a nickel, right? And for some reason, I believe Ellis has a nickel. If I could, and I can't do that if the room is empty, right? If you say, point to the person that has a nickel, if there's no one to point to, I cannot do it. So it's not insane to say that if the room is empty, if there's nobody around and we're doing an or, then false would be a reasonable default assumption. If there are no balls in the jar, I can't point to a red ball. So I can't say there exists a red ball in the jar. So we have true as the default for and false as the default for or. So that was sort of a long answer, Josh. Did that help?
Yeah, that did.
Cool. Other questions about the quiz or about other things related to the quiz? The quiz is due tomorrow. So if people have questions about it, definitely holler. Oh, and once again, I forgot to make it so you could see your grades on the quiz until Josh pointed that out. And so I think that's now fixed, but I don't know what I did there. So hopefully that's better now. Questions? Okay. A couple of bookkeeping things. If you're some people have used the sign up thing for signing up for office hours. If you just don't understand what's happening with that link, if that page doesn't make sense to you or doesn't work for you, definitely let me know. A couple of people have used it, so at least it sort of works. But you know, I don't know how much you folks have used Google Calendar. I don't know how familiar you are with what's going on there. So if you've got questions or you're having any problems, definitely let me know. So, and then the time codes on the video, those take quite a while. Probably for an hour lecture, it probably adds an hour of time on my part to go through and work out all the time codes. So there was clearly strong voting in favor of having them. So that's good, and I appreciate that. I'm gonna have to see if I can find a way to do that faster, better, because it was very time consuming. So I'll try to continue to do it, but at some point it may lose to the demands of life. But we'll try to keep it up while we can. So that's all the bookkeeping stuff I have. My plan for today, I didn't have a little outline slide, but we had ended Monday with exercise 9.3. I'd like to do exercise 9.7 as another example. And then I want to talk a little bit about instantiation, which is theorem 9.13, and Metatheorem 9.16, which is sort of weird and often confuses people. And then depending on how much time is left after that, we might move on and do another exercise or two, but we'll see how the time goes. So is that reasonable, folks? Cool? Questions? Okay, hearing none, moving forward. So I want a new page. Whoop. So I was going to do exercise 9.7. Find there we are. And we're using the typing because the tablet is hating me today because I had changed computers. Exercise 9.7, which is theorem 9.10. And this is a range weakening strengthening rule. Which says that for all x, q, or r, so we've got an or in the range, okay, p, implies for all x, q, p. So this is saying that we can, if we have an or in the range, we can say that that implies one of the for all with one of the pieces in the range. So if we know that something's true for people that are either computer science or math majors, then we know it's true for computer science majors. Okay, that's what that's telling us. Okay, so I'm going to start with the left-hand side because it's got more stuff in it. It has the R. If I started with the right-hand side, I'd have to invent the R somewhere, and that doesn't seem like that's going to be a very fun thing to have to do. So we're going to start with the left-hand side. And now, at this point, I'm going to use range split for idempotent. So if you remember, there were these three range split rules in chapter 8 that all have an or in the range. And we've got 8.16, 17, and 18. And one of the really nice things is that in chapter 9, we're almost always doing quantifications that are, whoa, oh, come on. Am I still in the meeting? Can somebody confirm?
You're still in the meeting.
Oh, weird. Because my computer just told me I logged out of Zoom. And that freaked me out a little bit. But apparently, I'm still in the meeting. So we're going to call it good and move on. I hate computers. So 16, 17, and 18 are all range split. And 8.18 is range split for idempotent. And that's really nice because in chapter 9, everything is either and or, and or are both idempotent. So we can use 8.18 often in chapter 9. And here's a good example. So we'll use 8.18 range split for idempotent, noting that and is idempotent. And so 8.18 says that we can take something with an or in the range like this, and we can break it up into two quantifications, each of which have one of the pieces in the range. So we'll have a Q quantification and an R quantification. And how are those two quantifications joined? They're joined with whatever the star operator is. So if this is a for all, that means we're using and. So we and these two things together. So are we cool with why that's an and there when we're doing for alls? Is that okie dokie? Questions? Not hearing any. Then this was a nice move because notice this is exactly what we want over here on the right hand side. So we've just got two pieces and we want one of them. And we've seen some rules that allow us to throw things away and introduce implications. And that would be what we would use. And another hint that this would be useful is we're proving a weakening strengthening rule in chapter 9, which often means we're going to want to use a weakening strengthening rule from chapter 3. And that's exactly what we're looking for, is we're looking for one of the 3, 7, 6 weakening strengthening rules. So in particular, we want 376b. 376b, weakening strengthening, which says that an and of two things, in this case, this thing and this thing, implies either one of them. And we want the Q1. Boom. And so that gets us, we started here. So we started here, which is the left-hand side. And here, So we started here, which is the left-hand side. And it was equivalent to this, which then implied that, which is the right-hand side. So by transitivity, the left-hand side implies the right-hand side, and we're done. And this shows an example of using a chapter 8 rule and using a chapter 3 rule to get to where we want to go. Somebody was going to ask a question, I think. No? I thought I heard a noise. Any questions about this example?
I was curious, in general, what does implies mean in the world of computer science and programming?
Oh, that's an interesting question.
Or if it's too much, we could do office hours about it too.
Well, I mean, that's a fair question. I think if what I'll say a little bit here. If what I say isn't super helpful, then maybe we should take it to office hours. I think, without having thought hard about this, I think that implies doesn't come up a lot actually in computer science directly, but implies comes up a lot in human thinking. And because computing is almost always at some level a formalization of some sort of human thought, we need to be able to take implication when it exists in human thinking and understand it and do appropriate things with it when we formalize that human thinking in the logic like this or in programming. So I don't know that that's super helpful, but there aren't kind of implication constructs in programming languages. Like and or exist, equals exists and will do the right thing on Boolean. So you kind of have equivals as an operator in most programming languages. But I don't know any programming language that has an operator that's like implies. I mean, I'm sure there are some. Actually, Prolog, in a weird way, kind of does implication, but that's really out on the fringes of the universe and not something you're likely to ever work with. So I think the short answer is it doesn't show up a lot in programming, but it shows up a lot in people's heads. And so we need to be able to work with it because a lot of what we're doing is trying to formalize the thinking human beings have and turn that into logic, in this case, code in sort of more programming context. I don't know, did that make any sense?
Yeah, that makes sense.
Okay, and like I said, if you found that unsatisfactory, feel free to follow up. And if I think about it more, maybe I'll come up with a more clever, snappy answer than like, well, I don't know, which is sort of what you got. But yeah, I don't have anything much more profound to say than that. Other questions?
So for 818, it said that we had to that numbers had to be finite. Do we have to do anything to check for that, or is that just kind of like implied with the proofs?
Oh, that's actually a great question. Now let me find 818. So and I want to make sure I was looking at the printed thing, but I want to make sure I look at the textbook as well, because sometimes the printed thing and the textbook say slightly different things. Okay, so you must be reading the printed list of theorems?
Yeah, I'm reading off the printed one.
Gotcha. Because it says something slightly different in the book. And this is often a source of confusion. Luckily, we don't have to care a great deal, but it's good that you brought it up, and we can try to clean it up a little bit here. So I'm going to make a new page. So the book says, so 818, the book says, provided each quantification is defined, and then goes on to provide the actual theorem. Oh, so, and this is the book. And then the all theorems list, its constraints on 818 are provided P is of type Boolean, and I'm going to write out Boolean because I can't really make that funky B here, or R and S are finite, ... And then both of them provide the rule itself, which is star X, R or S P equals star X. And again, I'm using star for star, not star for multiplication, because I don't have a star character. SP. Okay. So that's the rule. And the book sort of has this constraint, and the all theorems has this constraint. And those are different, and you could legitimately be like, who's right? What do these even mean? So the concern is, if the range is infinite and the operator doesn't work well over certain infinite ranges, then you can have quantifications that are not defined. And there's a footnote about this in the book, but it's easy to miss it. And so as an example, if I said, oh, I don't know, 0 at most I. So that would be 0 plus 1 plus 2 plus 3 plus forever. Okay. So I'm adding I up for all I that are at least 0, which is 0 plus 1 plus 2 plus 3 on to infinity. That's not defined. So this isn't, I guess maybe I should make my arrow go the other way. This isn't defined because it doesn't have a finite value. Okay. So that's when the book talks about quantifications being defined, they're trying to rule out that kind of case, because it turns out infinity is tricky in math and needs to be handled very carefully. I mean, without getting into the weeds, a lot of the history of math in the late 1800s and early 1900s was basically very smart mathematicians having complete panic attacks about whether math was even valid and worked, in large part because in the late 1800s, people started to take infinity seriously as a thing. And then people went, oh, but if we do that, we can make all kinds of paradoxes and break a lot of things. And holy moly, it seems like we've just destroyed the world. And that kind of caused a lot of people to panic. And so there are, reams of paper were spent on trying to understand exactly how to handle infinity properly. And so that's way above our pay grade. That moves more into calculus, as in Calc 1, 2, 3, Newtonian calculus. But even there, they probably are hand-waving over a lot of the details of infinities. And it would be a more advanced math class that would get into that in a serious way. So the book just says, provided each quantification is defined, without really opening that box up and talking about what that would mean. Now, Warford, the guy that wrote the all theorems thing, who's a faculty member who uses this book at another institution, very nice guy, met him once. Warford changed some things to try to make it a little more precise what this vague, each quantification is defined thing means. And that's where this provided P is Boolean or R and S are finite. Now, this is really overly strict. You can have defined quantifications that don't have these properties. But again, I think that's beyond our pay grade, and Warford was just trying to simplify things down to the cases that were most likely to come up in the book. And so the two cases that are most likely to come up in the book are, first, that P is Boolean. If the body of the quantification is a Boolean valued expression, then we don't have to worry about using 8.18. We're just good, okay? And so if we back up to here we are okay. This has to have, this has to have a Boolean value. Oh, stop it, come here. P has to have a Boolean value because we're anding up the values of P. We're saying P with one value and P with another value and P with another value. and that only makes sense if the p's are all Booleans. So in this case, we can use 818 because p is Boolean. So we could add that, and p is Boolean as a note if we wanted to be careful about, yes, it's okay to use 818 in this case. Because the bodies have to be Booleans for either for all or exists, pretty much all of chapter 9, 818 is fair game because the body will be Boolean valued. And so we don't have to worry about it. That's gonna, save us. We can be a little sloppy about that part of 818 because in chapter 9, the body of a for all is always Boolean. The body of an exists is always Boolean. So we can be like, everything's good. We can use 818. Go team. And then the other option is that this or this business that says either, or both R and S are finite. And that actually is just saying that these ranges both have to be finite. So that's to disallow this sort of case where we have an infinite range. And so it would just go forever and we can't sort it out. If we have infinite ranges, then you have to get into limits and all this calculus stuff, and they just don't want to get into that. So there would be cases you could use 818 with infinite R or S if you knew things about the limits, but that really is not what this class is about. So that's how to read this. Either we can use 818 if we know that P is Boolean, or P is not Boolean, but we know that R and S are finite. If either of those two things are true, then it's legal to use 818. Since the only idempotent operators we're likely to use very often are and or, and or have to have bodies that are Boolean, we can usually just use 818 because we're using and or. This other part would really only come up if we got into like min and max doing complicated things, and we're not likely to do that. So that was a long answer to that question, but I hope that helped a little.
No, yeah, thank you. That was perfect.
Cool. Other questions? Great questions so far. I like questions. Anything else? Okay, then I was going to find my notes, make sure I'm, so we did 9.7. So yeah, so now I wanted to talk about instantiation 9.13, which often confuses people. We talked about this some in Dojo last night. Oh, I haven't posted the Dojo video yet. I'll try to do that shortly after class when I post this one. But it has some stuff about instantiation as well there. So we've got, it's Theorem 9.13, instantiation. And what does that say? That says that if we have for all x p, and notice the range has to be empty, which is another way of saying that there's the word true in here. That if we have for all xp, then that implies p with x replaced by e for any expression e that has the right type. I mean, you couldn't, like, if x is supposed to be a number, you can't put a lawn chair there, but ignoring the, I mean, assuming the typing stuff is right, you can put any expression e there. And this frequently sort of muddles people in two ways, like A, what does it mean? So we'll talk about that, but also how do you use it? And that was a lot of what happened in Dojo last night. And we'll talk about that a little bit today too. and more if there are questions. So what does it mean? Well, let's look at an example. Let's say we know that I squared is at least 0 for any I in, say, the real numbers. So even if I is negative, if you square it, you get a positive or a non-zero value. So that would let us say that I squared at least 0 is true for I replaced by anything that's a reasonable, real valued thing. So we could be like 3z divided by w, okay, where I'm assuming z and w are real valued something or others. So actually, let me do this way. So that would be true by 9.13. And then we could do the substitution. Textual substitution. And we would get 3 times z. Oh, sorry about that. I need to make sure my notifications are turned off because apparently people are trying to talk to me. Oh, stop it. So that's that. And I've got an extra paren here on the left I don't need. So that would be textual substitution. And then, you know, we could do more stuff. But this is just saying if we know this is true for all I, then we know it's true for any particular value, okay? And that's really what instantiation gives us, is it says, if we know something's true for everything, then we know it's true for any particular something, okay? If I know every human being has DNA, okay, then I know that Noah has DNA, on the assumption Noah's not an alien, right? I mean, so there's some assumptions being made there, but let's go with the fact that Noah's a perfectly good card-carrying human being. And
let's
so
not
then,
make any assumptions here, all right?
Well, I'm sorry, you know, we'll go with it temporarily. I'm not trying to reveal your secret identity. If every human being has DNA, then Noah has DNA because Noah is a human being, right? If every number, if the square of every number is greater than or equal to 0, the square of this particular number is greater than or equal to 0. The square of 7 is greater than or equal to 0, right? The square of pi is greater than or equal to 0. So we can kind of put whatever value we want in there. And so this is a way of getting outside the for all, right? If we've got a for all like this, but we want to, what we need is a particular value, this allows us to make the for all go away and give us instead the thing we want for a particular value. And this will, the use of this will become important at the end of chapter 9. There's a bunch of word problems. And if you love the word problems in chapter 5, oh man, these in chapter 9 are really going to make you happy because they're very complicated and weird. And we'll definitely spend time talking about them. And there'll be a number of examples where instantiation turns out to be important, that we'll know something is true for everything. And so then that tells us that something's true for a particular value. So that's the basic setup for instantiation. We'll do more with it later in chapter 9. And it will, so we'll come back to it and it will become more, I think, more clear, hopefully. But this is relevant in the quiz. One of the quiz problems is essentially an instantiation question. So, questions about that? Going. Then, oh, go ahead.
Gone.
Good job. So then the other thing I was going to talk about today is 9.16, which is a metatheorem. So it's not a theorem. It's not a move we can make in the game. It's a statement about the game. And Metatheorem 9.16 says, P is a theorem if and only if for all x, P is a theorem. So that one's a little weird. And it's kind of the reverse in some sense of instantiation. Not really, but they're related if you squint. So this is saying a statement is a theorem if and only if you can for all any of the variables in that statement and have a theorem. So I could say I squared is greater than or equal to 0 is a theorem if and only if for all I squared is greater than 0, at least 0, is a theorem. So, and we would often say things like this. We would say I squared is at least 0. And what we don't say explicitly, but what we imply in that is I squared is at least 0 for every I, right? If we say people have DNA, we are implicitly saying all people, for all, P in the set of people, P has DNA, right? We just don't tend to say the for all part all the time. Sometimes we do, but we don't do it super consistently. And so when we say something like this without a quantifier, what we typically mean is the quantified version. So to formalize a statement, if I were to write, if I wrote or said I squared is at least 0, what I probably mean is for, or let's say all, we'll just say for all I squared is at least 0, right? So I'm implicitly talking about a quantifier. So does that make sense? Questions about that? And there's a question in chat from Richard, which I'll get to in a hot sec, so hang on. How you would use this is a fair question. It will come up more, again, later in chapter 9 when we get to the word problems. But we'll sometimes have proofs that have something like, let I be an arbitrary integer, then blah, 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 and eventually, P of I is true. So we do some stuff and then we eventually prove that P of I is true, whatever P of I is. Then because P of I is true for arbitrary I, we can use 9.16 to conclude that for all I, P of I is true. Since we didn't make any assumptions about what I was, like we didn't say it was positive or it was even or it was less than 5 or anything like that, and we were able to show that P of I was true, whatever that was, then we know that we can use 9.16 to conclude that for all I, P of I is true. That's how it tends to get used. We'll see examples that'll be clearer, I think, later in the chapter. But questions about that before I answer the question I've got in chat? Okay. So then there's a question in chat about what does it mean to have the range be true? So let's say, and I think this is sort of what does a true range mean? Actually, is often a source of confusion. What does it mean to have the range be true when doing math? So as an example, if I have, oops. If I have this, that's equivalent to, but because we're just using this abbreviation, to having the range be true. Okay, and I'm doing a little guessing here, and so correct me if I'm guessing wrong, but I think people sometimes get confused because this is a Boolean and we're doing things with numbers, and what exactly is going on with that and how does this get interpreted. And so one thing to be clear about is if we have some operator, so this is the generic quantification. If we have the generic quantification, this is always Boolean. And this has to have the same type that makes sense with the operator. So let me type that. And actually we'll say range is always Boolean, and body has a type that is appropriate for the operator star. Wow. And so this is saying the range is saying which values of the variable x in this case, I in this case, are we going to look at? And it's the variables that make the range true, or the values that make the range true. Well, any value makes true, true, right? It doesn't, every value of I makes true, true, because true doesn't depend on I, right? So this is a way of saying we're going to take all of the i's, every I from minus infinity to plus infinity, and we're saying that for all of them, this is going to be true. We could, in certain circumstances, we might want to say things that are more constrained. So it's not the case. So this is not correct. Like that's just not true, because there are I where I squared is bigger than 100. 10, I squared is equal to 100, which would make this false. But I could add a range that is more limiting, and I could say that if I is between minus 10 and 10, then it's true that I squared is less than 100. And so we're only going to look at the I that make this true, and we're only going to check them here. And so with this range, that's going to be true. If I put true there, then this is not going to be true, because there are I's that are big, too big, and we square them, they're going to be bigger than 100. So I have no idea if that helped. Hopefully that was useful. Other questions? Going, gone. Okay. So, oh, there's my notes. La, 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 la. Well, let's see. What do we got? We got a little over 10 minutes. Let's start 9.20. Oh, no, let's do 9.1, exercise 915. That's shorter. Yeah, that'll be a better choice. Okay. And then we'll do the other one later because it's a longer one. We'll do it Friday. So we're going to do exercise 915, which is Theorem 919. And it is, oh, and here it's an exist. So this is our first exist theorem. And of course I'm typing. And there really is not a great way to do a backwards E here. So I'll just do a forwards E. I mean, you can hopefully mentally swap these two things. So exists X R P equivals exists X R and colon R and P. Okay. And so this is a trading theorem similar to, actually I could even say this is a trading theorem. Trading. So this is similar to the trading theorems for all, and we looked at some of those on Monday. So we're moving something that was in the range over to the body. So this says if there is something that makes R true and makes P true, then there exists something that makes R and P true, which sort of makes sense. Like if there is somebody in 1302 that has a nickel, then there is somebody who is in 1302 and has a nickel. Okay. So questions about the setup before we do the proof? Okay. So I will start with the left-hand side for no particularly great reason. You could argue I should start from the right-hand side because it's got an and in it. It doesn't really matter, do I think? Well, actually, let's start with the right-hand side. I'll do it. We'll live boldly, and we'll go because I do think there is an argument that the right-hand side has more structure. So now, in the early stages of the exist part, we don't have a lot of options other than to use definition elimination as our first step. So this is like when we first introduced implication in chapter 3. Pretty much every implication rule started by getting rid of implication because we didn't have any rules that did things with it. And so in this case, similar thing, we don't have much to go on. And so probably the first thing we have to do is get rid of the exists. And the sort of standard way to convert an exists into a for all, because we have rules about for all, are the generalized De Morgan rules. So there's an axiom, which is 9.17, and then there are 3 theorems that are easily provable from 9.17 in 9.18, A, B, and C. So I'll just use 9.17. Generalized De Morgan. And generalized De Morgan says we get a negation on the outside. We flip the exists to a for all. And we negate the body, not the range. This has no effect on the range, but we negate the body. So this generalized De Morgan says if there exists an X that makes this true, that it must be the case that not all X make that false. So if there is someone who has a nickel, then it's not true that everybody doesn't have a nickel. Okay, sort of weird. I mean, you get into all this double negation and the linguistics goes crazy. But that's what we're talking about here. So you to go from an exists to a for all like this, you put a negation in the front and you negate the body. And the 3 in chapter 8, or sorry, the 3 in 9.18 give you versions where the negation's in front of the exist instead of in front of the for all. And move the other negations around a little bit, but it's all pretty much the same game. Okay, so questions about that? Okay, now at this point, we don't have a lot to work with, but we're potentially able to use De Morgan here. So regular chapter 3 De Morgan, if we're using generalized De Morgan, it often comes up that regular chapter 3 De Morgan is relevant in circumstances. So we'll try that. So that's 347A De Morgan. And it tells us, so let's see, this part all stays the same. It says the negation of an and is the negation of the pieces ORed together. So we flip the and to an or, and we negate the 2 parts. So R becomes not R, and P becomes not P. Okay? Questions? Now, we're trying to prove a trading rule about exists, which means we're likely to need one of the trading rules about for all to get there. And there's a bunch of them, right? I mean, there's Axiom 9.2, there's 3 versions in Theorem 9.3, and there's 4 versions in Theorem 9.4. So many possibilities. So looking at where we're headed, we're trying to get the R into the body, and we've got an or here. And so I think actually 9.3a looks like a win. So I'm going to actually type 9.3a over here. Oops, yeah. So 9.3a says, for all x RP, that's equivalent to for all x, yeah, not R, oops, colon, not R or P. And that's really nice, right? Because this part here looks very similar. So this part here looks quite similar to what we've got here. And there's a little noise. We've got this not out here. Well, that can just carry forward. We just let it go. For all x, that matches. Vertical bar colon, that matches. Not R, that matches. Or P. Well, that means we've got a not P, so we're going to have to substitute a not P in here to make this match. But if we replace P with not P in this theorem, then this part matches this here very nicely. And so we can use that 9.3a trading. And then negation just hangs around waiting for its time to be our friend. And now we'll use 9.3a to move the not R into the range. So we're moving, oops, that was weird. There we go. We're moving, oh, stop it. There we go. We're moving this part over here. And so in our case, that means we're moving this part into the range here. Okay, does that make sense? Questions about that?
I have a question.
Sure.
Why does the not come with the R? Because in the 9.3a formula, like not R just becomes R.
Oh, you're completely right. There would not be a not there. Good catch. My bad. You're right. The not disappears when we move it into the range. So this not was supposed to go away. So thank you, Josh, for catching that. And that would be important to the finish, because if I didn't do that, I would have ended up with a not R, and that wouldn't match where I was headed. So I would have hopefully eventually noticed, because I would have gotten to the end and had a not there and been, oh my God, what did I do? But you just saved us all from that confusion. So thank you, Josh. Other questions? Corrections? Okay. So then now we've gotten to here. We're trying to get to here. And that actually is just generalized De Morgan again. So generalized De Morgan says we can, if we go from an exist to a for all, we put a negation out front and we negate the body. Well, we can just do it in the reverse order and take away the negation here, take away the negation here, and turn that into an exist. So we'll just use 9.17 again, but in the other direction. So this is a pretty classic definition elimination. We eliminated the exist, manipulated, and then including using a rule similar to the kind of thing we're trying to prove. We're trying to prove a trading rule. So we used a trading rule in the other space about for alls, and then we use the same rule to reintroduce the exist at the end. So we have exist X, and this is where we would have had a problem, because we would have had a not R here if Josh hadn't corrected my mistake, and then that wouldn't have matched and it would have been bad. But as it is, everything's fine because Josh saved us. And we get that we get over here to the left-hand side and everything matches and we're good. And that proves Theorem 9.19. Questions about that? We've got about 1 minute left. Questions about that? Questions about anything?
I guess I have. Oh, you can go.
Thank you. For scheduling office hours, do we just put it on your Google Doc, and then does it have to be like on your office hours on Monday, Tuesday, Friday, or?
No. So I shared a link. Let me, got too many things going on here. Momentary pause. I shared a link on Canvas that, and it's also shared in Slack, but on, actually, let me actually do this. I'm gonna stop sharing this, and I'm gonna instead share this. So this should be I should be sharing the Canvas for the class. So I've updated this part here. So it's got the link to use to get to the Zoom. It's got the Google Doc that's got all of the recordings on it. And it also has a link to the sign up page. So if you go there, you should see something like this, where instead of all this blue, it'll have your calendar if you use Google Calendar. If you don't, it'll all just be blank. But if you use Google Calendar, your schedule will show up here. But you'll also see all of these appointment boxes. And those are all spots where you could reserve a half hour of office hours. So if you just click on a box, then you get something like this, and you can put in a description if you want, but you don't have to. If there was something particular you knew you wanted to talk about, you could tell me that, but it's not at all important. All you need to do is hit save. And if you hit save, then that slot will disappear from the list of available slots. It will show up on my calendar with your name on it, so I'll know you signed up for it. I will get an email about it, and some other notifications will happen. So the world will yell at me saying, Opti picked a slot. And I'll be able to be like, great, I knew that. And so I'll know to look forward to that being a thing. So if you do that, then that's awesome. If you use Google Calendar, it will also put that event on your calendar. If you don't use Google Calendar, it'll still put it on your calendar, but you'll just never know. It's like a tree falling in a forest, and no one was there to see it. But that's what would happen if you click one of those things. Does that make sense?
Yeah, it does. I was also wondering, do we just join this Zoom, or is there like a different Zoom we join for the office hours?
So I will need to make a Zoom for office hours. So when you book an appointment, I will create a Zoom for that appointment so that your appointment's not this, because if we all had the same Zoom, anybody could walk in the middle of your office hours, and that would be weird and awkward. So I'll make a separate Zoom for each office hours. So when you book one, I'll create a Zoom link and it'll get added to that calendar entry, but I'll also send you an email about it. So Google Calendar will send you an email with the Zoom information. So you should just be able to join that.
Okay, thank you.
Other questions in the -3 minutes remaining?
Yeah, I guess I have just one question. Can you use for all like theorems when and is the main operator?
Yes.
Okay.
So for all is just another way of writing and exists is just another way of writing or. So if you're oring a bunch of stuff together, that's essentially an exists. And if you're anding a bunch of stuff together, that's essentially a for all. Does that make sense?
Yeah, that makes sense.
Cool. Anything else in the -4 minutes that are remaining? Cool. Well, thank you all very much. I will see everybody on Friday. The quiz is due Thursday night. Let me know if you've got any questions or concerns. Otherwise, we'll see you later. Thanks a lot. Bye.